In this video, we're going to look at some definite integral properties, okay? And how we're going to do that for this example is first we're going to graph the integrand. And what the integrand is in this question is the absolute value of 1/2 x minus 4. So that's our function that we're going to need to graph. And then we're going to use known area formulas to evaluate the given definite integral. What we talked about last video in the average value of a function video, what we're going to look at is we're going to look at ways of how we can translate this definite integral into area formulas to calculate the area under our curve, because that's what a definite integral really gives us, right? Is the area under some curve. And when we say under, we mean beneath the curve and above the x-axis, right? So like the x-axis serves as almost a boundary and the curve serves the other one. So what we're going to do first is we're going to look at graphing this thing. So graphing absolute value gets kind of tricky because we don't really know like a good starting spot. And the reason why I say that is because the absolute value, what it does is we're essentially going to graph the thing we're taking the absolute value of, but then we're going to make sure that all the function values are positive. So what I'm going to do, and is like how I like to start graphing absolute value, is I'm going to take 1/2 x minus 4 as like a linear equation and graph it because it's in slope-intercept form. And then I'm going to find where we have to make all the values positive. And it'll make a little bit more sense what I'm talking about as we do it. So first what I'm going to do, like I said, is I'm going to graph 1/2 x minus 4. So we start with minus 4 there is our y-intercept, right? So we use our slope of 1/2 to go up 1 to the right 2. We're going to keep going in this nature because we've got to get all the way to 13, right? So we're going to be graphing for a little bit. But we're not going to take too long because we're going over by counts of 2, right? So here we're going to go up 1/2. We go up 1/2, up 1/2, up 1/2. And then we're going to need to go up a couple more. So we go up 1/2. Then we go up 1/2. That's a little bit kind of skewed there. Let's see where we're at. 2, 4, 6, 8, 10, 12. We need one more. So here we're going to go up 1/2. So this is actually going to be 14, right? So what we're going to be dealing with is we're going to kind of get a fractional value because what we're dealing with is the interval from 13 and then we want 6. So something right here, right? But let's look at how we're going to graph this that we just did as an absolute value. We know that when we look at graphing absolute value, they always look something like this, right? They're always having to be positive. In this case, that's what it's going to be. It's like the function's values are only going to exist for positive y's, right? Because there's no number being added or subtracted outside of the absolute value that would shift our stuff below the x-axis, okay? So what we're dealing with is we need to find out where this function value starts at 0, and then essentially what we're going to do is we're going to take all the positive values that get graphed after that for what they are. So those are going to be fine, and this is going to be the endpoint of our interval right here. But then what we're going to do for all of these that would be negative values, we're going to reflect them above the x-axis so that whenever we plug in one of these numbers and we get a function value that would be negative, we would take the absolute value of it, and that absolute value would evaluate to be its positive counterpart. Okay, does that make sense? So what we're dealing with is, say we plug in 6 into our equation, which we're going to do here in a little bit. What we're going to get is 1/2 times 6 gives us 3, minus 4 gives us -1, which is the function's value in 1/2 x minus 4, but when we take the absolute value of -1, we get +1, right? So essentially what we're doing is we're reflecting all these negative function values above the x-axis so that we can take the absolute value of our function, right? So this value at x equals 4 is going to be +2, 2 is going to be +3, and then we're going to have something like 0, 4. So then what we're actually going to have for our absolute value is something that looks more like this, and pardon my bad drawing, that was horrible. But what we're looking for now is, now that we've graphed 1/2 x minus 4, right? This is our function that we've graphed. We're looking to calculate the area between the curve from 6 to 13, okay? So now that we have our function graphed, what we need to look at is looking how we can calculate the area between the curve of our function and the x-axis, right? So we need to look at what we have made between 6 and 13. Well, we see that we have this shape going from 6 to 8. It's kind of like a small triangle, right? So we have a triangle here, and then if we go from 8 to 13, we also have another triangle there, right? So what we're going to end up having is we're going to have the area of this triangle plus the area of this triangle, right? So what we're going to do is to find the area under our curve and above the x-axis is we're going to find the area of this triangle and the area of this triangle, add them together, and that will give us the area under the curve, okay? So let's think about how to find the area of our different triangles. And we know that our formula here is base times height, right? But let's think about what our base and height values are going to be for these given triangles, okay? So we can kind of argue here that our base is going to be the distance that the triangle takes along the x-axis, right? So here in this case, for triangle 1, our base is going to be 2, and then here, for triangle 2, we're going to have a distance of 5. Right? And that makes sense because the length of our interval 6 to 13 is 7, right? And 5 plus 2 gives us 7. So we said that our first triangle's base is 2, and that our second triangle's base length was 5. So we have those values going on there. But now we need to try to find the height of our triangles, right? And just like we've seen in previous examples of stuff that we've done, the height of our triangle here is going to be given to us by our function's value at 13, right? Because we start at 0, and then we go all the way up to the curve here. So what f of 13 is going to give us is the height of our triangle, and then similarly, f of 6 is going to give us the height of our first triangle, right? So let's evaluate those real quick. Let's evaluate f of 6 up here, and we'll evaluate f of 13 down here. So we have f of 13. So we have absolute value of 1/2 times 6 minus 4. This equals the absolute value of 3 minus 4, or absolute value negative 1, which gives us positive 1. Okay? So we said that f of 6 was going to be height 1, right? The height of our first triangle. So the area formula for our triangle 1 is going to be 1/2 times the base, which is 2, and then times the height, which we found to be 1. Okay? And then we said that f of 13 is going to be our second height. So let's calculate f of 13. So we get absolute value of 1/2 times 13 minus 4. So this gives us the absolute value of 13 over 2 minus, and this minus 4 is going to translate to an 8 over 2 by finding a common denominator, right? And then we get the absolute value of 5 over 2, which is just 5 over 2. So our height 2, or our function's value at 13, is 5 over 2. So now what we have is the area for triangle 1 given as a formula and the area for triangle 2 given as a formula, right? Well, let's do some substitution of what this is going to turn into using all this stuff, and let's see what we kind of get here. So we said that by figuring out what shapes the area under our curve takes between the curve and the x-axis, we can add those areas together instead of calculating our definite integral, right? So what we're doing is really just translating the definite integral we were given into the areas that we found over here, right? So this equals the area of triangle 1 plus the area of triangle 2. So now that we know our definite integral that we were given translates to area of triangle 1 plus area of triangle 2 that we found, let's make those substitutions, do those calculations, and figure out what we get. So area of triangle 1 was 1/2 times 2 times 1, right? And then area of triangle 2, we got 1/2 times 5 halves. So let's do all this multiplication. Let's simplify to figure out what this integral evaluates to. So here, 1/2 times 2 is 1, times 1 is 1. That was simple enough. But then here, we get 5 halves times 5 halves, right? And this becomes 1 plus 25 over 4. Or if we change 1 to have a common denominator there of over 4, we're going to translate that to 4 over 4. So this becomes 29 over 4. So our definite integral from 6 to 13 of this integrand that we had evaluates to 29 over 4, and we found that by saying that this definite integral is denoted by the area of our first triangle that we found and the area of our second triangle that we found, right? So we found the area under this curve of absolute value of 1/2 x minus 4 from 6 to 13 by breaking the area between the curve and the x-axis up into two different triangles and then finding their areas and adding them together. Okay? So we use some known area formulas here to evaluate this given definite integral in the way that we just talked about, right? We graphed it and we figured out what shapes that the areas take between the curve and the x-axis given on these bounds that we have here of 6 to 13. And we used our knowledge of stuff that we've done before, area formulas we've seen before, and kind of all these other things kind of culminating into evaluating a definite integral.